In this video, we're going to talk about how to find the area underneath a curve. So let's draw a curve. We'll start by drawing our xy axes, like so. And now we'll draw some random curve. Let's call this y equals f of x. I'm interested in computing the area underneath the curve. Now, in order to do that, I need to specify a range of values over which we're considering this function. So let's start over here and call that x equal to a, and on the other side we'll call it b. So what we want to do is we want to find or compute the area underneath the curve between x equals a and x equals b. So the region in question is this region here, the region underneath the curve and above the x-axis. In this picture, notice that f is positive, and that's what we want. We want f of x to be greater than, or at least equal to 0, for all x in this interval, from a to b. So a is less than x is less than or equal to b. And our objective is to determine or compute or estimate the area underneath that curve. The way that we're going to do it is by approximating the area using rectangles. So let me just copy and paste this region so that we can work with it a little bit. So the first thing I'm going to do is I'm going to divide my interval from a to b into a bunch of subintervals. So divide the interval from a to b into n subintervals. One, two, three, four, dot, 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 n. So what I'm going to do is I'm going to call the first x value, which is a, I'm going to call that x0, and then x1, x2, x3, and so on until we get to x sub n right there. Let me put a little dot, dot, dot here. I'm specifying n intervals. I don't know what n is, but n is going to be any positive integer. And what I want to do is I want to construct some rectangles that have as base these line segments going from x0 to x1, x1 to x2, x2 to x3, and so on. Now, how wide are all of these intervals? Well, it depends on how many of them there are, but they're all the same. We call the length of these intervals delta x. Delta x is used to mean a small change in x. So delta x is the distance between x1 and x0, or between x2 and x1, and so on. We're going to divide the interval up into n subintervals, all of equal length. So delta x is going to be the same for all of these intervals. All of these intervals will have the same width. We can actually figure out what that width is because we know that the total length of the interval is b minus a. So delta x is equal to b minus a, which is the total length of the interval, divided by how many subintervals there are. So we divide it by n. That tells us the width of all of these intervals. Now I want to construct rectangles over all of these intervals. So how am I going to do that? I'm going to use the right sums or the left sums, or approximations if you prefer. So for example, let's use r sub n. That r sub n be the right endpoint sum, or approximation if you prefer, using n rectangles. So what that means is I'm going to determine the height of these rectangles using the right endpoint. So on our first interval, from 0 to 1, my right endpoint is x1, and so I just go straight up until I hit the curve, like so, and that determines the height of the rectangle. That's my first rectangle. Then from x1 to x2, the right endpoint is x2. So again, I just go straight to the curve, and however high that is, that gives me the height of the rectangle, and so on. So between x2 and x3, I choose the right endpoint, x3. The height of the rectangle is determined by the distance up to the curve, and that gives me my third rectangle. And I keep going like this until I run out. And in the end, I'll have n rectangles. So R sub n is the sum of all of the areas of these rectangles. Now, all of these rectangles are the same width, which is delta x. So width delta x times the height. Now, what is the height of the first rectangle? Well, it's determined by the distance between the x-axis and the curve. But that's exactly the y value. And what is y? Y is equal to f of x. So this point right here above x1 has coordinates x1, comma, f of x1. F of x1 is exactly my y value. And the y value tells me how high up I am. So the height of this rectangle is f of x1. And we continue in this way. The second one has width delta x, and the height is f of x2. And we keep going like this until we get to our last interval, which has height f of b, or f of x sub n, like so. So that's going to be delta x times f of x sub n. Generally, we factor out the delta x, so we can write this as f of x sub 1 plus f of x sub 2, and so on until we get to the last one, f of x sub n. And all of this is multiplied by delta x. We're also allowed to use summation notation, in which case we have r sub capital N is equal to the sum. So we write the sigma symbol, the Greek letter sigma, and the things that we're adding up look at like f at x for some index I times delta x, and I goes from 1 to n. We're adding up n objects. This is the right hand or right endpoint approximation, or the right endpoint sum. Similarly, we can use the left endpoint sum. So L sub n is the left endpoint. Sometimes it's called the left hand sum. Left endpoint sum, again, or approximation, if you prefer, using n rectangles. In this case, ln, you use the left endpoints. So it's going to be f at x0, which is our leftmost endpoint. Our leftmost endpoint is x sub 0. So the left endpoint is x0, so we evaluate f at x0 to get our height times delta x, plus f at x1 times delta x, and so on, until the very last one, which is not x sub n, but x sub n minus 1, delta x. And using summation notation, we write sigma I equals 1 to, not I equals 1, rather it's I equals 0 to n minus 1 of f of xi delta x. Now, if you prefer to sum from 1 to n, you can do that. Sum I equals 1 to n, but that means instead of summing x sub I, you're summing x sub I minus 1 delta x. If you start writing these out, when I is equal to 1, you get f at x sub 0 delta x, and so on. The last value of I is n, so you end up with f at x sub n minus 1 delta x. So it's okay to sum it from I equals 1 to n, provided you change the x sub I to x sub I minus 1. So now here we have our right endpoint sum and our left endpoint sum. And the theorem says that provided f is continuous, so if f is continuous on this interval from a to b, then the area under y equals f of x between x equals a and x equals b is area equals the limit as capital N goes to infinity of r sub n, or, if you prefer, the limit as n goes to infinity of L sub n. We won't be proving this theorem, but the basic idea is that as n gets larger, you're fitting more and more rectangles underneath the curve, and they begin to approximate the shape of the curve better and better. Let's just go back up to our picture here. Let me just grab this, copy it, and let me paste it down here so we can look at it again. So as I said, the idea is that as n gets smaller, or rather larger, the size of these rectangles gets smaller and smaller. So what we could do, for example, is we could further divide each one of these intervals in half. And if we did that, we'd get a better fit, like so. These rectangles don't give a perfect fit, but they fit better than previously. And the more rectangles you use, the thinner they become and the better they fit underneath the curve. Now notice that some of these rectangles are above the curve and some are below. Let me just paste it again. Some of these are all rectangles made using the right endpoint. But notice that some of these rectangles are a little too big and some are a little too small. So the right endpoint approximation, or the right endpoint sum, won't always give you an upper estimate or a lower estimate. In this particular case, we can't be sure if Rn is too big or too small. All we know is that it's getting close to the actual value. When your function is increasing, like it is here, you always end up with Rn being an upper estimate. Let's draw a picture. So if I have a curve which is always increasing, like this one, that one's always increasing. So if I divide this interval up into a bunch of subintervals, you can see that the right endpoint is always going to give you something which is too big. like so. So if f is increasing, like it is in this example, r sub n is always too big. So it's giving you an overestimate. On the other hand, if you have a decreasing function, so let's draw one of those now. Let's draw a decreasing function. Let's say this one. This is decreasing. And if we divide our interval up into smaller intervals, you can see here that the right endpoint is going to give you something which is too small. All of these are completely contained underneath the graph. So if f is decreasing, Rn is too small, an underestimate. And the statements are reversed for ln. If you start with an increasing function and you look at ln with the left endpoints, then you'll always be underneath, like so. So in this case, ln is an underestimate. And if your function is decreasing, then ln will give you an overestimate, like this. All of these are above the graph, so it's too big. So ln is an overestimate. This is only true if your function is increasing or decreasing. If we go back to our original example, you see here we have a function which is both increasing and then decreasing and then increasing again. So our right endpoints give you rectangles which first are too big, then are too small, and then are too big again. Another common choice for point in an interval is the midpoint. So you can also use the midpoint to get an approximation. M sub n is the midpoint sum or approximation using n rectangles. In this case, you're looking at an interval like so, and of course you divide it x0, x1, x2, x3, and so on. And in this case, you want to choose the midpoint. The midpoint between x0 and x1 is x0 plus x1 over 2. It's the average. Similarly, between x1 and x2, it's x1 plus x2 over 2, and so on. Between x2 and x3, it's x2 plus x3 over 2. And at the end here, if we're allowed to go all the way, we have x sub n, and here we have x sub n minus 1. So x sub n minus 1 and x sub n, the midpoint is x sub n minus 1 plus x sub n over 2. Now, don't forget that x sub 0 is actually a, and x sub n is actually b, but sometimes it's just more convenient to write them in terms of their index. Well, in that case, m sub n is going to be equal to, well, now the height of your rectangle is determined by the function evaluated at the midpoint. So it's f at x0 plus x1 over 2, and the height is still delta x. So it's delta x. Then plus f evaluated at the midpoint. But again, the midpoint is x1 plus x2 over 2 delta x, and so on until you get to the end. Now, in this case, the end is the interval from between x sub n minus 1 and x sub n. So it's going to be f evaluated at the midpoint, x sub n minus 1 plus x sub n over 2 times delta x. So this is a very common approximation that's used, especially when a function is neither increasing or decreasing. But it's not necessarily any better to use mn, ln, or rn, because as our theorem stated, so recall from our theorem from up here, if we scroll back, if f is a continuous function on your interval from a to b, then the area between x equals a and x equals b is equal to the limit as n goes to infinity of r sub n, which is equal to the limit as n goes to infinity of L sub n, and indeed it's equal to the limit as n goes to infinity of M sub n. So theorem, and it's the same hypothesis. If f is continuous on the interval from a to b, then the area underneath the curve between x equals a and x equals b is equal to the limit as capital N goes to infinity of M sub n. So it doesn't really matter which one you use, ln or rn or mn. Any one of those three will get you there in the end. And in fact, it doesn't matter what point you pick in that interval. You can pick any point that you want, because in fact, these intervals are all getting smaller and smaller as n goes to infinity. And since the intervals are getting smaller and smaller, the left endpoint and the right endpoint and the midpoint are getting closer and closer and closer to each other. And in fact, all of the points in these intervals, because the intervals are shrinking, the left endpoint and the right endpoint get close to each other, and so all the points inside get close to each other too. So it doesn't really matter what point you pick, but the left endpoint and the right endpoint and the midpoint are all convenient choices. They're easy to find, they're easy to compute, especially if you're using a computer. In practice, computing these limits is very difficult. So usually what you do is just simply approximate the area by choosing a large enough value for n. Let's write that down. So in practice, we approximate the area by choosing a large value for n. Because the fact is that these limits are very difficult to compute in most cases. There are some simple cases where we can compute the limit exactly, and let's do one of those now, just so we can verify that the method does work the way that we think it should work. So let's look at an example. So for this example, we're going to choose one of the easiest functions, which is f of x equals x. So find the area under y equals x from x equals 0 to x equals 1. All right, let's look at this on a graph. Now this is the line y equals x, so that line looks like this. So let's say that this is 1 over here, which means that this is 1 on the y-axis. What we want to do is we want to compute the area underneath the curve between x equals 0 and 1. Now, you might notice that that's actually a triangle. It's a triangle where the base is equal to 1 and the height is also equal to 1. So we actually know what the area of this is. The area is 1/2 the base times the height, which is just 1/2. So we already know the area here, but let's use our technique that we've just developed to compute the area in this particular example. All right, well, I'm going to stick to the right-hand sums. So we will use r sub n. All right, so let me just copy and paste this again. And let's get rid of these extra ones. So what I want to do is I want to divide this interval into n subintervals. Now, I don't actually know what n is going to be. So the idea is we're just going to, that will be x1, this will be x2, this will be x3, and so on. So if I'm using the right sum, then what that tells me is my first interval will go from 0 to x1, and we'll use the right endpoint to determine the height. Between x1 and x2, the right endpoint is x2, so again, that gives us the height. This graph is y equals x, so the height is just the x value. So our first rectangle has height x1, and our second rectangle has height x2. And if we did the third one, we use the right endpoint, and we can see that it's going to have height x3. So if we decide to write down r sub n, it's going to be equal to, well, let's see, what is delta x? We can actually compute that. So delta x is equal to b minus a divided by n. It's just 1 over n. But let's leave it as delta x for the time being. So r sub n is going to be f at x1 times delta x plus f at x2 times delta x, and so on until we get to the last term, which is f at x sub n delta x. Now, it's probably going to be easier to write this out in summation notation, but before we do that, we'll just remark that f at x1 is, of course, x1, because the thing we're looking at here is y is equal to x. So f at x2 is x2, and f at xn is xn. So we can write this out. R sub n is x1 delta x plus x2 delta x, and so on until we get to x sub n delta x, like that. All right, well, we actually know what x1, x2, x3, x4, and all of those are, because we know that delta x is equal to 1 over n. So that means that this length is 1 over n. This length is also 1 over n. This length is also 1 over n, and so on. So that means if I just copy and paste this one more time, we can actually identify what all of these x values really are. So let me just get rid of all of those. Well, we know what this last one is. It's 1. The first one is 1 over n. Then the second one is 2 over n. The third one is 3 over n. And I know this because I know that all of these are delta x. All these widths are delta x. And I know what delta x is. Delta x is 1 over n. Delta x is 1 over n. So the first one is 0 plus 1 over n. And then if I add 1 over n to that, I get 2 over n. Then if I add 1 over n to that, I get 3 over n, and so on. So if I want to add all of these up, I'm going to get 1 over n delta x plus 2 over n delta x, and so on until I get to the last one, which is n over n delta x. Of course, n over n is just 1. I could factor out this delta x, and then we have Rn is equal to 1 over n plus 2 over n plus 3 over n, all the way until I get to n over n. Let me just fix my handwriting there. It's a little bit sloppy. Dot, 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 n over n times delta x. All right. Now, the next thing I can do is I can factor out all of these n's. So I'm going to have that r sub n is equal to, I'm going to factor out that 1 over n, and I'm left with 1 plus 2 plus 3 plus 4, and so on, up to n. Now what is delta x? It's 1 over n. So I have 1 over n times 1 over n, which of course is 1 over n squared. So this is going to be r sub n is equal to 1 plus 2 plus 3, and so on, till I get to n times 1 over n squared. Now, in the parentheses here, I have the sum of the first n positive integers, and there's a formula for that. The value of that is n times n plus 1 over 2. So that means that r sub n is equal to n times n plus 1 over 2 times 1 over n squared. Now this n is going to cancel with one of those n's, and what that means is that r sub n is equal to n plus 1 over 2 times n. This is the nth sum, or the nth approximation, using the right endpoints. And we know that the area, the actual area under the curve, is the limit as n goes to infinity of r sub n. But we actually have a formula for r sub n. The limit as n goes to infinity of n plus 1 over 2 times n. Let me just factor out that 1/2. So we have 1/2 times n plus 1 over n. Now this n plus 1 over n, that's actually an indeterminate form, but these are the kind that we know how to compute. This thing right here goes to 1. So this is actually just 1/2 times 1, which is 1/2. So the area underneath the curve between 0 and 1 is 1/2, which of course we already knew. But this does verify that our method gives us the right answer, the answer that we expect.